Today's topic is Kirchoffs laws. So it's also pronounced as Kirchoffs laws or Kirchoffs laws. Anyway, it can be pronounced. So Kirchhoff is the name of a scientist. So he gave two very powerful laws in current electricity, using which it's possible to find out electric current or resistance or even potential difference. Actually, all the three quantities, electric current. So we know. So already we have seen Ohm's law. So I'm just drawing a very simple rough column. So the simple equation, Ohm's law equation, V is equal to IR. Using the Ohm's law, it is possible, supposing potential difference V, it's also called as voltage. If voltage and resistance are given, current can be determined. So if two quantities are given, the third quantity actually can be determined with the help of the Ohm's law. So Ohm's law is actually applicable for very simple circuits, like a single loop circuit, a simple circuit consisting of a battery, a resistor. So this is a simple circuit. EMF of the battery is E. So in such cases of very simple circuits like a single loop circuit, Ohm's law can be very easily applied. Now supposing it's a more complicated circuit. So for example, here it's not a single loop. So just see this point. At this point, two conductors are meeting. It's not two conductors, but many conductors are taken here. One more conductor, one more conductor, one more conductor. And another more complicated situation is this is a single loop. So here, supposing that one more resistance is connected here this way. In between, one more resistance is connected this way. And in between, again, here between these two, one more cell is connected this way. A cell, another cell. And here in between, another resistance. That way, it's a mesh of different resistances, a network of different resistances, different components, not just resistances, resistance, cell, etc. So in such more complicated situations, more complicated networks of different components, it's very difficult to apply the very simple Ohm's law. In such cases, two very powerful laws help in finding out any unknown current or say unknown resistance or unknown potential difference. So those are two laws were actually given by Kirchoff. Kirchoff's first law, it's also called as Kirchoffs Current Law or Kirchoffs Junction Theorem. And next, there is another law, second law called as Kirchoffs Voltage Law. Now, firstly, seeing the Kirchoff's first law. Now, Kirchoff's current law, from the name itself, it gives a simple relation between currents. Now, consider a number of conductors. Now, here just we have seen here already. So, a very simple circuit, like a single loop circuit, actually resistance is connected to a battery. So, at a single point, two different components are actually connected, or two different conductors are connected. So, this is a wire coming from a resistance, and this is a wire coming from a battery or a cell. Both are connected. So instead of two conductors, consider many conductors like this. This is one conductor this way, another conductor this way, and another conductor this way. So another conductor this way, another conductor. So at this point, many connectors are actually connected together. So this point is simply called as junction of different conductors. So in the first conductor, a current I1 is flowing. In the second conductor, a current I2 is flowing. Now, both the currents, you can see that they are actually flowing towards the junction. And a third current, I3, in the third conductor is actually flowing away from the junction. And next, I4, next, I5. So when many conductors are meeting at a point, the common point where number of conductors meet is simply called as a junction. So Kirchoff's current law actually gives a simple relation using which all these currents actually can be connected. We can get a simple equation. It's also called as Kirchoff's first law because it's related to a junction where a number of connectors are meeting. That's why it's also called as Kirchoff's junction theorem. Now this is nothing but directly obtained from the law of conservation of energy, that is law of conservation of charge. It's a direct consequence of the law of conservation of charge itself. So another way which Kirchoff's current law can be named is, it's also called as law of conservation of charge, but mostly in general it's called as Kirchoff's current law only. KCL. So KCL, just remember the short form KCL, Kirchoffs Current Law. So it's nothing but a modified form of the or a direct consequence of the law of conservation of charge. Now, according to law of conservation of charge, so we have three very powerful conservation laws: law of conservation of mass, law of conservation of energy. We have seen these two laws long back, almost in the conservation of mass. We have been seeing almost from the sixth class or seventh class, sixth grade or seventh grade, like that. Next, conservation of energy, most probably, firstly, you have learned in ninth class. And next, law of conservation of charge. This also you have learned somewhere in the 10th class. So these are very powerful laws, conservation laws. So it's a direct consequence of the law of conservation of charge itself. So according to the law, total charge in a closed system always remains constant. Charge can neither be created nor destroyed, and the total charge in a closed system remains constant. That's a simple form of the law of conservation of charge. So now consider the same thing here. Now, how this is a Kirchoffs current law. It's directly obtained from the law of conservation of charge. So it can be understood like this. Now consider here, at this point, five conductors are actually meeting. Now this, if it is seen in a magnifying glass, it looks like this, somewhat like this. I'll just draw this in the rough column. So only for the sake of understanding, I'm considering. So this is the first conductor, say. So this is the first conductor, and this is the second conductor. So through the first conductor, current I1 is flowing. Through the second conductor, current I2 is flowing. Just a moment, please. I'll just make a small adjustment here. Through the second conductor, current I2 is flowing. So this way. So now these two conductors are meeting here. So the same thing I have drawn, I1 and I2. Just imagining that it's actually much more magnified, seeing that in a magnifying glass. Now at this particular point, they're actually at this end, right and left ends, currents are actually starting from somewhere at the left end of the conductor, first conductor, and similarly the bottom end of the second conductor, current is starting. The top ends are actually joined together, and then again three more conductors are joined here this way. So this is one conductor. Next, this is the other conductor. Next, this is the other conductor this way. So I'll do one thing, I'll just shade this. So for the sake of understanding, I'm just shading them, the conductors. So now I'll again, because too many lines actually. So simple lines are very simple to understand. Now for the sake of complete proof, I'm just showing them as thick conductors. So this is the third conductor, fourth conductor, and fifth conductor. Now this is much more clearer. Now it can be seen that both these conductors, I1 and I2 conductors, the first and second conductors, they are meeting at the top end. And then here, the two conductors are becoming three conductors. The third conductor, fourth conductor, and the fifth conductor. So I think the diagram is clearer. Okay. So now, so the first two conductors currents are I1 and I2. So this is a much more magnified form of the same diagram. So junction where actually two conductors are meeting and in which currents are actually flowing towards the junction, and three conductors are also meeting here at the same junction at the same point where currents I3, I4 and I5 are flowing away from the junction. So this is how in the magnified form, simplest form, magnified form of the diagram looks like. Magnified form even can be more complicated also, but I have taken the simplest form. Once this is understood, how the law of conservation of charge can be applied here in this case can be understood in every complicated situation also. Complicated junctions also, the same thing can be applied. There won't be any complication. So I1, I2 flowing towards the junction, the meeting, the region or the point or the region where number of connectors are meeting is simply called as junction here. And I3, this is I3 and this is I4 and this is finally I5. So I3, I4, I5 are moving currents which are directed away from the junction where the five conductors are actually meeting. Now can be seen that at this is the cross section of total cross section of the first two conductors, and this is also the total common cross section of the next three conductors. That's how it can be, the magnified form can be clearly seen. Now how to apply the law of conservation of charge. Now just observe here, the current I1 is actually flowing into the cross section here, the big cross section where the first two, which is actually the total cross section of both the first and second conductors together, and also the third, fourth and fifth conductors together. That's how the magnified form of the diagram can be seen. So imagine that due to this current I1, a charge Q1 is flowing out of this cross section. A charge Q1 is flowing. So this charge Q1, so I'll just write it here. So actually there's no place here. So I'll just draw a rough column here. So the charge which is flowing out of this cross section, this particular cross section which I am showing with the cursor, observe the cursor compulsorily, flowing out in a given time, say 1 second is say Q1. Now in the same 1 second, through the second cross section, second conductor, through the same cross section, the charge flowing out, let it be called as Q2. The total charge the total charge is actually flowing out of this cross section, which I am showing with the cursor, where all the 5 conductors are actually really meeting, is Q1 plus Q2. So in 1 second, total charge flowing out of this particular cross section is Q1 plus Q2. So once the charge Q1 plus Q2 is flowing out of this cross section, earlier before this 1 second, it was actually, before it started flowing out of this cross section, it was actually on the left side of the cross section. At the end of 1 second, the entire charge Q1 plus Q2 is on the right side. But it is actually divided among the 3 conductors, third, fourth and fifth conductors. Now consider this particular cross section of the third conductor. The charge which is actually flowing out of this particular cross section of the third conductor, call it as Q3. In that same 1 second time, it has flown out of it has entered the third conductor. So in that same 1 second time interval, the charge is actually flowing into the conductor, the fourth conductor, call it as Q4. And in that same 1 second, the charge is actually entering into the fifth conductor, call it as Q5. So the total charge which has actually entered all these 3 conductors is Q3 plus Q4 plus Q5. Like this it can be written. So now consider this particular cross section, which is actually the common cross section for almost, it's like the cross section where all the 5, it's not exactly common cross section, but it's a cross section at which all the 5 conductors are actually meeting. The total charge entering this cross section or entering this junction is what? Q1 plus Q2 in a time of 1 second. And the total charge, which is actually same charge Q1 plus Q2, is actually dividing into 3 different parts. It's actually now split into not just 2 parts but 3 parts, Q3 plus Q4 plus Q5. So whatever charge that is entering, suppose 10 coulombs of charge is entering this cross section, at the end of 1 second, this 10 coulombs of charge has completely flown out of this cross section. So that 10 coulombs is now divided into 3 parts. But charge entering is 10 coulombs Q1 plus Q2. Charge leaving the cross section is also 10 coulombs Q3 plus Q4 plus Q5. So from law of conservation of charge, so whatever charge that is entering this cross section, the same charge is actually again leaving this particular cross section in this particular given time interval. So whatever things we are seeing here are simple, nowhere any complication is there. So from law of conservation of charge, initial charge is equal to final charge, because at this particular cross section no other charge from outside is coming here and no charge is from here, it's actually going outside. Only it's actually limited only to this particular arrangement of the conductors, and no charge is actually getting created here and no charge is getting destroyed. So from law of conservation of charge, charge should be remaining constant. So initial charge, that means charge which is entering the cross section, should be equal to the final charge, the charge which is leaving the cross section, which is actually this particular Q3 plus Q4 plus Q5. So from law of conservation of charge, simply we can say that Q1 plus Q2 is equal to Q3 plus Q4 plus Q5. But these charges that are actually entering the cross section Q1 and Q2 are taking place in how much time? 1 second. But charge flowing in unit time is nothing but current only. So Q1 is the charge flowing through this particular cross section. Just observe the cursor compulsory. Through this particular cross section in unit time is nothing but current. So Q1 is nothing but I1, and charge Q2 is what? Flowing through this particular cross section in unit time is nothing but current I2 itself, from definition of electric current. What is electric current? It's defined as charge flowing in unit time. The same way Q3 is what? The charge which is actually flowing through this cross section upwards in unit time. That's nothing but current I3 itself. So this Q3 is I3, the same way Q4 is I4, Q5 is I5. So we can also say that I1 plus I2 is equal to I3 plus I4 plus I5. That's what we are getting. So the total current, total charge entering the junction, which is nothing but total current itself. That's what we got. Q1 plus Q2 is nothing but I1 plus I2. So directly we can write this. It's in a simple manner. So whatever things we are seeing here are simple. Nowhere any complication is there. So in the diagram, so total current entering the junction, that is sum of the currents entering the junction, is equal to total current leaving this particular junction. That means the cross section where all the conductors are meeting is now we are treating it as junction. The total current leaving the junction is what? Q3 plus Q4 plus Q5 or I3 plus I4 plus I5. So I3 plus I4 plus I5. This itself is called as the Kirchoffs current law. So statement is very simple, directly based on the law of conservation of charge. The sum of currents entering a junction is exactly equal to the sum of the currents leaving the junction. That itself is called as Kirchoffs current law or Kirchoffs first law or Kirchoffs junction theorem, because it's related to junction, the point or the region where a number of conductors are meeting. So statement is very simple. The statement is very simple. The sum of currents entering a junction is equal to sum of currents leaving the junction. So directly we are taking from the statement, applying the statement to this particular situation of 5 conductors meeting at the junction O, we are getting this particular equation. So the equation is very simple, directly following from the statement. So I'm not writing the statement because it takes some time. So while explaining how to write the running notes, I'll give the statement. I'll write the statement more clearly, or directly I'll show the written statement without any wastage of time. I'll not change anything, only the statement will be coming here. So that's about the Kirchoffs current first law or Kirchoffs current law or Kirchoffs junction theorem. So it's entirely based on the law of conservation of charge. Now using the main purpose of this law is supposing supposing a few currents are known, supposing out of total 5 currents, 4 currents are known, the 5th current can be determined, or at any junction a number of currents are present. The exact relation between all the currents can be known with the help of this particular equation or with the help of the first law. And next, how to find out the voltage or resistance, that's another thing. So not using Kirchoffs current law, we can mainly get currents, any unknown current is there, or what is the relation between known currents and unknown currents. In such cases the law will be useful. But how to find out any potential difference or voltage V and resistance, for that reason the Kirchoffs, the voltage law, the second law should be applied. Now what is Kirchoffs voltage law or second law? So I'm just this is the heading actually. Now this is a very important topic, Kirchoffs laws. I did not show the marks here. So it carries in the board exam, it actually comes under a short answer question carrying about say 4 marks or say 3 marks, or only statements means it can be given even for 2 marks also, only statements without much explanation. The explanation is also asked, it can be asked for full 4 marks. It has very important applications, very powerful applications. Big essay questions are actually based on this particular topic, Kirchoffs laws. So now coming into the second law. The second law statement, I'll just carry it upwards. Just a moment please, I'll just I'm just carrying it a little upwards. Okay, now what does the voltage law state? Now voltage law is mainly applicable for a closed circuit or a closed loop belonging to any complicated network of electrical components like resistors, cells or batteries. A number of components are actually connected to form many loops. So here one loop, just observe the same diagram again. Here there is one loop, here this is one loop, and this is another loop. So like that, a third loop, a fourth loop, many loops. For each loop or each closed loop or each closed circuit, which is actually a part of many other closed circuits, for each loop the law is actually separately applicable. Now I'll take a very simple situation. So for example, a closed circuit or a closed loop consisting of say a few cells and a few resistors like this. Now this is say a resistor, and next I'm taking a combination of a resistor and a cell. This is the negative terminal of the cell, positive terminal of the cell. So next again I'm taking another cell combined with a resistor, say. So resistor I'll take it here. This is again negative terminal, positive terminal. I'll shift the diagram a little upwards. So as complicated as possible, I'm taking the circuit. This way, and a separate resistor. Now here for each cell a separate resistor, a small resistor is shown. It actually denotes the internal resistance of the cell. Now let this separate resistor. So this is actually a part of this is a closed loop. It's actually a part of a much more bigger mesh of different resistors and cells. So this way current can be flowing in any direction. So this is a resistor R1. This is a cell of EMF E1. Its internal resistance is denoted as R1. So strictly speaking, internal resistance will be inside the cell. But just for the sake of convenience, the internal resistance, as we have seen in Ohm's law, simple applications and problems of Ohm's law, the internal resistance is actually much more convenient to draw it outside so that it can be applied, the Ohm's law can be applied more easily. So the same convention is followed here. The internal resistance is just shown outside so that it's more easier to apply the laws and write the equations. So any doubt is there, the real life situation should be considered. So internal resistance belongs to the cell. Inside it should be imagined. Any complication comes. Otherwise, very easily the same thing can be followed. So always it must be remembered, reality, internal resistance belongs to the cell inside. So for convenience, we are just showing it outside. Always this followed in electrical circuits. So that, and one more cell is there. Its EMF is E2. Its internal resistance is R2. Now here, this is a regular resistor. Its resistance is denoted as capital R1. So it's not related to any cell. And another resistor is there, R2. So current flow through this resistor is I1. Next, to the second part, current it is called as I2. Through the third part, current is I3. And next, finally, through the fourth part, the current is I4. Now this closed loop is denoted as A, B, C, D. Now in this, just see here, it's not just a complete simple single loop circuit. It's a part of a mesh or a network of different resistors and cells. Outside here, one more can be seen. A small part of a conductor is shown. It's a small part of another circuit. Here it can be closed here, consisting of many cells and resistors. All that is not important. So once a single closed loop is considered, for that part only the law is applicable. Separately, for every closed loop separately, the law is really proved to be applicable. Now this is also directly proved from, again, the same thing, another very powerful law, conservation law. Already we have seen current law is based on law of conservation of charge. Now here the voltage law is directly proved from the law of conservation of energy when it is applied to electric field. Now inside each conductor, current is flowing. Current flow is nothing but flow of charges. How can a charge move? Charge moves only because of the electrical force acting on the charge inside an electric field. So inside each conductor, electric field exists. So always in electric field, when law of conservation of energy is applied, using the very important properties of electric field, we'll be getting a very simple result. Now that result we have already seen in static electricity. Now very important property of electric field. Electric field is called as a conservative field. based on the conservative nature of the electric field, the law is actually proved. The Kirchoffs voltage law is actually proved. So now here, just see here. So here some current is flowing towards the junction B. Again at the junction C, current can be flowing into the junction or away from the junction. Anything can be possible. So that's not important. So what is inside the circuit only is important now for us. So again here the current can be either into the junction or away from the junction, it doesn't matter. So it's outside the circuit. So only anyway direction it can be shown. The thing is it should be so whether it is into the junction or away from the junction, it should be having some meaning. For example, all the three currents cannot be towards the junction. At least one should be away from the junction. That way, that following that convention, roughly the diagram can be drawn. So now the important thing is, what does the Kirchoff's voltage law simply state? Now, based on the conservative nature of the electric field, which is actually really present inside each conductor here and including the cell, so inside cell also electric field is present. So electric field, based on its conservative nature, it is proved that the Kirchoff's voltage law is actually proved. Now you start at any point on the closed loop. So closed loop is simply known as A, B, C, D. Closed means if we start at the point A, supposing we are going say round the loop or round the circuit in the clockwise direction, say in this direction, we start at A, next go to B, next to C, next to D, again we can come back to A. So the closed loop is denoted as A, B, C, D, A. So we are starting at A and again coming back to A again. This is called as complete traveling. We are going around the circuit completely once. This is simply called as complete traveling or complete traversal of the circuit. Now as we travel around the circuit completely once, from A to B, there is a potential difference or potential difference across AB. How it is determined? Using Ohm's law. Always potential difference across the resistor is given by current into resistance. Already we have seen this equation, Ohm's law. It's a very powerful law. So applying Ohm's law, we can easily find out the potential difference. So potential difference is also called as difference of potentials. So always in electric field, at every point there will be having some potential at every point. So in this electric field also there will be some potential. At potential there will be some potential value at A and there is a potential value at B. So the difference of these potentials itself is called as potential difference, and that potential difference from Ohm's law is given by current into resistance. So as we go from A to B, there is a change in there is a difference of potential. This difference of potential is also called as change in potential. So from A to B, there is some change in potential. Again from B to C, there is another change in potential, and again from C to D, again there is some change in potential. Using Ohm's law, we can easily find out. For a resistor, using Ohm's law, we can easily find out the change in potential or potential difference. And using the definition of EMF, we can even find out the change in potential when we are going across a cell also, based on the definition of EMF. So simple, what we are seeing here is very simple usage of definitions and laws. How definition of EMF is used here, immediately in the next step it will be coming. But now the important thing is the change in potential across resistor we are getting from Ohm's law, and using definition of EMF we can get the change in potential as we go from one end of a cell to the other end of the cell. So this way the change in potential or difference of potential or potential difference across each and every component in the complete loop can be determined separately. So from A to B, what is the change in potential? B to C, what is the change in potential? And from C to D, totally, what is the change in potential? And from D to A, what is the change in potential? So each change in potential or each potential difference easily we can find out. Now the law simply states that the sum of all these changes in potential, each change in potential or potential difference symbol is simply V. Potential difference regular symbol is what? Simply V. So first potential difference across AB can be called as V1. Second potential difference, it can be taken as V2. Third potential difference, V3. Fourth potential difference, V4, like that. So add up all these potential differences. It's called as sum of all the potential differences or sum of all the changes in potentials. Now the law simply states that the sum of all these changes in potentials or sum of all the potential differences in a complete closed loop or in a complete traversal of a closed loop is exactly equal to 0. It is exactly equal to 0. Now how this comes? Why the sum of all these potentials is exactly, or sum of all the changes in potentials or sum of all the PDs, potential differences, is exactly 0? This directly follows from the conservative nature of the electric field. What is the meaning of conservative nature of electric field? Already you have learnt the conservative nature of gravitational field previously. So the same thing is actually applicable here. Conservative nature simply has only one simple meaning. It's just in the form of a single sentence. Based on that, this actually can be proved. So, but one small thing is, just observe here. Now we have here in the circuit across each part there is a potential difference. So V1, V2, V3, V4 like that. In more complicated, bigger circuits, V4, V5, many potential differences will be there. When we are adding up all of them, we are getting 0. How can a number of values be 0? This is possible only when some values are positive, some values are negative. Then only their sum will be exactly. All of them are positive means they only will get added up. So they'll never get cancelled. So this means that some potential differences or some changes in potential, say V1, V2 are positive. Next V3, V4 can be, must be negative. Then only all of them will be getting cancelled equal to 0. So such a sum, such an addition of a number of values, by taking into consideration their signs, whether they are positive or negative, everything is taken into consideration, then they are added so that they get cancelled completely. Such a sum is simply called as algebraic sum. So from this we are getting the complete statement of the Kirchoffs voltage law. Simply states that the algebraic sum of all the changes in potentials in a closed loop, or the algebraic sum of all the potential differences in a closed loop, or the algebraic sum of all the potential differences in a complete traversal of a closed loop. So this is a big statement, but in short it can be stated as very simple. The algebraic sum of all the potential differences in a closed loop is 0. That's what the law states. So statement is very simple. So statement is very simple. The proof also will be not difficult. It also will be very simple. Already I said it's based on one simple fact, conservative nature of the electric field. Based on that it can be proved. So immediately next step only we'll be getting that. So statement is very simple. So I'm not writing the statements to save time. So immediately after the particular how to write this part. So this is a particular equation. Now this equation, now each potential difference we can substitute using the Ohm's law and the definition of EMF. So what is the first potential difference V1 across the resistor R1? It is I1 R1 like that. Based on that we can get the full form of this particular equation when it's applied to this particular simple circuit of this particular diagram, this particular example A, B, C, D, A. So this is general law when it is applied to this particular situation of two conductors and two cells with their internal resistances. What will be the form of the equation? That also should be written. That forms the complete law. That is complete explanation of the Kirchoffs voltage law. Now before that, now the important thing is why the sum of all these potential differences should be 0. The reason for this is, what is potential difference? Apply the definition of potential difference. Potential difference between 2 points is nothing but work done in driving a unit positive charge between the 2 points. That's how potential difference is defined. And what is EMF? EMF, we have seen that EMF definition is also somewhat similar. It is the work done by a cell or by the chemicals of the cell in driving a unit positive charge from the negative potential end or lower potential end of the cell to the positive potential end. This is the basic definition of EMF. This we have seen. So like that, EMF is a very important quantity related to any battery or a cell. It's a very important quantity. So basically it's defined as, basically EMF is actually defined from the law of conservation of energy. Based on the same law of conservation of energy, different definitions of EMF are actually obtained. Very simple definitions, but very powerful definitions. So those are actually applied here. Now just observe here. Now firstly we are going from A to B. So potential difference across AB, that means across the resistance R1, is what the work done in driving a unit positive charge from here to here. So now electric field is present in this entire closed loop. Now electric field is called as a conservative field. Now what is the meaning of a conservative field? Already you have learned that gravitational field is a conservative field. Now why gravitational field is called as a conservative field means, the basic reason is work done in moving a body or in moving a mass in a gravitational field between 2 points, it is completely independent of the path taken. It depends only on the initial and final position. That's what we have seen in gravitational field. It is independent of path. It depends only on the position. It's set to a position function and position dependent function, work done, and it is path independent function. So that is a very important property of that's the main property, not just very important, that's the main property of conservative field. Work done is path independent. It depends only on the positions, initial and final position. And one very important consequence of this path independence of work done is, supposing we start at a certain point in a gravitational field, when we take a body and move it along some path and again come back to the same point, the total work done will be coming to 0. This is a direct consequence of the conservative nature of the gravitational field. So electric field is also exactly like that. Electric field is also exactly like that. Whatever work that is done in moving a charge between 2 points, it is independent of the path taken. For example, from this point to some other point here, it is independent of the path, but it depends only on the initial and final positions. Now, based on that, again, whatever work that is done in moving a charge from a point A, going around a particular path, any path, and coming back to the same point. So we are just taking the charge from one point, going around some path and coming back to the same point. The total work done will be coming as 0. So now apply that here. So what is the work done in driving a unit pulse charge from A to B, go round the complete circuit once and again come back here? The total work done will be 0. What is this total work done? First A to B, work done W1. So but this work done is nothing but potential difference. The same way next, from B to C, the work done consists of two parts. Firstly, work done is across the internal resistance R1. This is nothing but potential difference across the internal resistance. We can easily find out using Ohm's law. Current into resistance. So what is the current here? I2 into resistance. They are visible clearly here. And next, through the cell, we are actually moving the unit pulse charge. Say from here to here. So we are just imagining that a unit pulse charge is actually moved. Any charge can be moved, but unit pulse charge is much more convenient, because we can directly apply the definition. So work done in moving unit pulse charge from here to here is nothing but potential difference between across AB, which is nothing but I1 R1. The same way I2 R1 will be getting I2 R1, small r1 that is. And next, from negative terminal of this cell to the positive terminal of the cell. Now inside this cell there is an electric field. What is the direction of the electric field? Easily we can guess. Always direction of electric field is from positive terminal to the negative. Inside the cell it is positive terminal to negative terminal, and outside the cell also it will be from positive terminal to negative terminal. But inside the cell, considering the direction, now here very powerful definition will be coming, the definition of EMF. So using the definition of EMF, there are totally five definitions. We have seen about 5 definitions, different definitions of EMFs. Using one particular definition, it's actually defined in terms of this electric field inside. The work done in driving unit pulse charge from negative terminal to positive terminal is actually done against that electric field, and that work done by definition of EMF is nothing but EMF itself. So here the work done in driving the unit pulse charge from here to here is nothing but EMF itself. And next, what is the next component here? We are reaching the end C, and from end C again we are going across a cell. Again the work, there is work done here in driving unit pulse charge from this terminal to this terminal. Observe the terminals. Now the signs now presently they are not important. We are just trying to get the proof of this equation. Proof, I said it's only one step, but the components being lengthy, but still we are not using anything complicated. Just Ohm's law we are using, definition of EMF, that's all. Again this work done here will be nothing but EMF itself. Next, through the resistor, what is the work done? Potential difference across this. So current is what here in this part? I3, in this branch I3 into R2. Next, across this current we know, resistance we know, we can get the potential difference. So what is the total work done? 0, because electric field is conservative field. And what is the total work done? Sum of all the works. Each work is nothing but a potential difference or EMF. Current into resistance across the resistor, and across the cell it is EMF. So that way we are getting that it's equal to 0. So the proof is very simple, no complication here. Everything, whatever things we are seeing here. So the only thing is, when we are trying to apply the definition or law in order to prove the particular statement of the new law. Now here, just observe here, the law is not a fundamental law. It's not a fundamental law because it's derived from other laws. Now current law is actually derived from law of conservation of charge, and the voltage law is actually derived from the conservative nature of the electric field, which is actually based on the conservative nature is actually a part of a law of conservation of energy. It's actually a part. It's based on concept of potential energy. Potential energy definition, measurement of potential energy, expression for derivation of the expression for gravitational potential energy. We have seen one very powerful law used. That is the law of conservation of energy. So the Kirchoffs voltage law is a direct consequence of the law of conservation of energy. It simply states that the algebraic sum of all the PDs, potential differences, or changes in potentials in a closed loop is exactly equal to 0. Now, the most important thing is how to apply this law in a given situation. Now, very simple thing is, we know how to measure the potential difference across each component, say resistor and also the cell. Resistor is nothing but current into resistance, Ohm's law. Cell is nothing but the EMF itself. But when it is positive, when it is negative, that also will not be complicated. That also will be very simple. Now, I'll just copy this diagram here, because the page is completed actually here. I'll just go to the next page. So I'll do one thing. I'll just copy the entire law itself, diagram, and also the equation of the voltage law. Now I'm going into the next page. So what we have seen is very simple. We got the equation for the voltage law. What is the equation? Very simple. Sigma V is equal to 0. And we have seen how it is actually applied in case of a closed loop. A very complicated closed loop we have taken. It's actually a part. In itself, it appears to be complicated, and also it's a part of a much more bigger complicated network of different components like resistors and cells. So we are just applying the law only for this particular closed loop. So now we are starting at A. So the loop should be mentioned. So we are starting at A and again ending at A again, going along the path A, B, C, D, A. So applying the voltage law for the loop. Okay, just a moment please. For the closed loop or for the closed circuit A, B, C, D, A. So whenever Kirchoff's voltage law is applied for a closed loop, we can go around the loop completely once in any direction. So actually in the diagram, we have taken the clockwise direction. Actually we can go in the reverse direction. So it doesn't matter whether this direction or this direction. The total work done at closed path by the conservative nature of the electric field is 0. It doesn't matter. So there won't be any difference at all. So now applying this, firstly, when we are going from A to B, so potential difference firstly we are taking. Now we are going in the direction of current. In the direction of current, always the potential difference or change in potential will be negative. What is the reason? Current always flows from higher potential to lower potential. So this is higher, this is lower. Higher potential is always denoted as positive. Lower potential is denoted as negative. So as we are going from A to B, that means this left end of the resistor to the right end, what is happening is initially we are at higher potential, finally we are at lower potential. What is the change in potential? Potential difference means change in potential. Change in potential is final minus initial. Always change in length is final length minus initial length. Change in area is final area minus initial area. Change in potential is what? Final potential minus initial. So final is lower, initial is higher. Lower minus higher is what? Negative. So first potential difference we are getting is negative. So it is, so V1 plus V2 plus V3 plus V4 plus V5, like that many potential differences are there here. First we are taking V1. So V1 is what? Potential difference we know from Ohm's law, it is I1 R1. It is very simple, I1 R1. But this potential difference we are just when we are going from A to B is coming as negative. The change in potential is coming as negative. That's all. So very simple. So we got the negative sign firstly. Next we are going from B to C. As we are going from B to C, firstly we are going through the across the internal resistance. Again in the direction of current. In the direction of current means what? Change in potential is negative, because in the direction of current means higher to lower we are going. So change will be final minus initial. So lower minus higher, it is negative. So minus I2 small r1. Next we are going across a cell. When we are going across the cell, we are going from lower terminal, negative terminal to the positive terminal, lower to higher. So change will be higher minus lower is what? Positive. So always change in potential difference across a cell is the potential difference across the electric field. Important thing is electric field here. So the potential difference across the electric field inside this cell terminals by one definition of EMF. We have seen that it is nothing but EMF itself. Now try to recollect all the definitions. Each and every definition of a EMF has its own importance. It has its own importance. So every definition, the basic definition is directly based on the law of conservation of energy. From that definition, we got all the other definitions. So using the definition of EMF, the potential difference here across the cell is nothing but EMF itself. But the EMF potential difference is positive or negative, means we are going from negative to positive. So change will be final minus initial always. Final is higher minus lower is what? Positive. So it is plus E1. So next we have reached C. Next C to D. C to D, first we are going across a cell. So cell, we are going from where, in which direction? Don't see the direction of current. Cell means only the terminals should be seen. Direction of current should be seen only for resistor. But cell, it doesn't work. Cell is electric field. Direction should be seen. So positive terminal, this is negative terminal. So what is the change in potential? We are going from positive to negative. So higher to lower. So change will be what? Final minus initial. Lower minus higher is what? Negative. It is minus. So potential difference is what? By definition of EMF, it is E2. Check the definition once again. Any doubt is there? Don't try to see that now. Don't try to check the doubts now. After listening to the class, you check it. Very easily from the definition we can get it. So definitions cannot be taken lightly. They were given by scientists. Nobody else gave the definitions. Only scientists have given. So based on a definition, we have derivations. Based on derivation results, that is, derivation result is another formula, new formula obtained from the original formula of the laws and definitions. We'll get another new formula. Based on that new formula and also different steps of the derivation, infinite number of problems will be set up. So problems are always obtained from the scientific derivation steps and also the results of the scientific derivation and definitions. So problems are actually, strictly speaking, they are nothing compared to scientific definitions and derivatives. So scientific definitions and derivatives were given only by few scientists. Only few scientists we had. From them only we got all the definitions. So they should not be taken lightly, because each and every problem, however complicated, it's entirely can be solved with the help of very simple definitions and laws. So so next we have gone across the cell of EMF E2. Next we are again going across the second internal resistance, but in the direction of current is what? The potential difference or change in potential is negative. Already we have seen it is negative minus. What is the potential difference across the internal resistance? Current into resistance. So I3R2. So next we have reached D, and from D we are again coming back to A. That means again the change in potential is what? Potential difference across the complete resistor R2. What is the potential difference across the complete resistance R2? We know Ohm's law, current into resistance, I4 into R2. But what is the potential difference? Is it positive or negative? We are going opposite the direction of current. Just see, this is the first time we are going opposite direction of current. Opposite direction of current means we are going from lower to higher. So because current flows from higher to lower, so we are going opposite, means we are going from lower to, this is lower potential, like negative potential, this is higher potential, like positive potential, similar to this one here. So the signs should not be shown here. So I'm just showing it for convenience. I'll remove them so if anybody is interested, I'll just put mark this using a different color. So most probably I'll just erase them. So yellow color I am marking. So it's not required in the exam. It need not be shown. Only as an example I'm showing. So this positive, this is negative. So change will be from, we are going from negative to positive. So change is from higher, that is final minus initial, final potential minus initial potential. Higher potential minus lower potential is what? Positive. So it is plus I4R2. It is what? Plus I4R2. That's all. So we have reached back A. So this is the algebraic sum of all the potential differences in the closed loop. That is sigma V's. That is equal to what? Simply 0. So that's what we are getting. So directly, no complication anywhere. Very simply we got the result. So that's all. This is the equation which directly we are getting by applying the very powerful voltage law, Kirchoffs voltage law, KVL. So now how to write the running notes? There's nothing, this is sufficient, this is the thing which has to be written. So now how to write the running notes? Running notes writing is very simple. There is not much explanation here. So all that, so it's directly we have to mention that it's based on the law of conservation of energy, the second law. First law is based on the law of conservation of charge. Not much. As simple as possible, the running notes must be written. So now this is the actual running notes. So already I prepared the running notes quickly. I'm showing to save time. So everything I kept as it is during the explanation. Diagrams, equations, everything. The only thing is between the diagram and the heading, I filled up the gap. That is the statement. The sum of currents entering the junction is equal to sum of the currents leaving the junction. So directly from figure at the junction now, applying the law, this equation. So it's based on the conservation of charge. So simple. Next, the second law, Kirchoffs voltage law. First statement, next equation, next explanation, based on the law of conservation of energy. So this is the running notes page. So just remember the minute. Most probably this minute is 48th minute or 47th minute. So keep this video to a pause here and take one or two snapshots, that is screenshots here, and take the entire running notes. It's very simple, no big explanation. Just entire explanation lies in the rough column in the form of diagrams. So while writing in the exam, very simple notes. One statement, one diagram, one equation. That's all. The same thing with the second law also. No big explanation. No conservative field nature of the electric field. All that explanation is skipped off in the running notes. See here. So no big explanation. So next page, just see. This is the next page. So after the statement and the equation, directly the diagram. Very simple diagram as it is. So next, how to get the equation, final equation from the diagram for this particular, from the law, applying the law from KVL. That's all. This is the completion of the running notes. Just within 2-3 minutes it can be completed. So quickly complete the running notes in the classwork and then attend the next class.